Hello and welcome to this introductory video on electric field lines and how to draw them. In this video we're going to introduce what they are, tell you conceptually what they're supposed to represent, hopefully give you an understanding of what that is, and then make sense out of our rules for how we draw them. So to set the stage, as we've been doing a lot in these videos on electrostatics and electric topics, we are again going to start off by thinking not about electricity, but about gravity. Now, when you think about the gravitational field of an object, or you think about gravity rather, you may not be thinking of it in terms of a gravitational field. You just think, oh, well, I know that if I'm sort of around the surface of the Earth, there's a nice acceleration that is due to gravity. But that fact that you can write that you can say that there's just sort of an acceleration, means that you are actually thinking about a gravitational field created by the one mass of the Earth. This big Earth, who cares what mass you're going to be using, whether it's the textbook that you're going to drop in some problem or a cannonball that you're shooting, it doesn't matter. You're just thinking about the fact that because the Earth is there, you know there's going to be an acceleration. So you can write something like that the force that some mass m, my little test mass, would actually experience is actually just given by m times this little g. And little g is this fundamental thing. It's the gravitational acceleration at the surface, say, of the Earth. It is describing the fact that just because the Earth is there, it's set up some sort of thing which exerts forces on all other masses. And that something that exerts those forces, that's what we mean by the gravitational field. So the gravitational field of the Earth is always there. It's just created by the Earth. And other masses move in response to that. Okay, so that's the sort of idea of having a gravitational field, as opposed to thinking about it being this force that's really the interaction between the two masses. We can say that the Earth sets up a gravitational field and the other masses react to it. And then similarly, in order to complete Newton's third law, we would say that the other masses, in turn, also have their own gravitational field, and that acts on the Earth. Okay. Now, little g, if you think back to our introduction of what the proper expression for the force of gravity is, that can be calculated from looking at that expression, and it's just g, the big G this time, so Newton's constant, Newton's gravitational constant, times the mass of the Earth, divided by, in this case, the distance to our second test mass, which, for instance, if we're putting on the surface of the Earth, that separation is just the radius of the Earth. So it's minus g times m divided by r squared. So that's everything from the force law except for the little m, because that's what we're going to use then to actually create the force. Okay, so we can describe this field very nicely in terms of the mass of the Earth, Newton's constant, and the size of the Earth. All right, and that's, as I say, all we're doing is taking the force law and dividing out by the little mass that we're using to test what that force is at some particular distance from the Earth. All right. Similarly, we had a force law which described the interaction of two charges, but you don't need to be talking about two charges. You can just talk about one charge. The moment that a charge is present, it will set up an electric field. And then other charges will move in response to how they interact with that electric field, just like we've done for gravity. All right, so it determines how the other charges will move, and exactly as we wrote before, so we've separated out the mass and the little gravitational field. We can write that the force on the particle is just the charge of the particle times this electric field through which it's moving. Okay, and again, we just go, and what is E? Well, E is just the force law divided by the charge on this test particle. So it's just K times Q, the charge of the thing generating the field, divided by our separation to its squared. And it's this time we're writing it as the full vector. We've got the r hat as well. So now let's talk about drawing the electric field lines. And as always, we're actually going to start with the gravitational case. It's a bit more intuitive, and then we'll see how we modify things to talk about charges and the electric field. So let's think about gravity And let's also quickly have a discussion of what it is that we'd like to convey in our drawings of field lines, what we mean by that. So we want to be able to create like a nice pictorial representation that includes information about which way something is going to move in that field and includes information about where the field is strongest. So where will we, as a test particle moving in this field, experience the largest force? All right, so let's think about a little bit. If we're doing gravity, we might have a little Earth here. We want to include information about how things move. So let's explore that a bit. If I put a mass here, it's just going to fall straight to the Earth. Put a mass here, straight to the Earth. So each time I'm just putting them at rest and asking what happens. Well, each time they're going to fall towards the Earth, just like that kind of thing. All right, and I could keep drawing it all the way around. Does that include information about the way things move? Absolutely. It's telling me exactly which way they would move. And does it include information about the strength? Well, let's think about this for a second. What is the gravitational field? Well, it's minus gm on r squared in the r hat direction. So it's just two constants divided by this separation, or the distance to where I'm testing the field, times this r hat direction. So that means that as r gets smaller, the field should get larger, and vice versa. As the r increases, the field should get smaller. So let's look at this. In here, compared to out here, I have very large separation of my field lines out here, and very small separation of the field lines, or the little arrows that I've drawn, inside, or closer to the Earth. So actually, we have indeed included information about the strength. So to sum up, what we've done with gravity is actually just drawn some lines toward the mass that's causing the field. That turns out correctly describes the direction that another mass would move as a result of that field. And further, we've seen that where the lines end up closer together, that precisely corresponds to regions where the field should be stronger. And therefore, we've got all the information that we wanted. Okay? So the little arrows are going to be our representation. Now, let's think about a charge. And let's go ahead and make it, say, a negative charge in the center. So we'll have an electron sitting here. And then let's think about testing it, say, with a proton. Well, a proton would, again, fall towards the charge. If we put it at rest, because our opposite charges attract. Okay, so we might have something like that for what a proton would do around an electron. But we have to think carefully as to whether that's going to work in general. So what if I flip the sign of the charge in the middle? If that was a proton, and I was testing it with a proton, then I'm in trouble because they should have been moving away. So we've got to think about that carefully. The strength is right because it's the same kind of thing. The electric field is basically just the K times the Q divided by r squared, r hat. Okay, so the electric field is just that. But as we said, these directions are dependent upon whether I mean an electron or a proton as my test charge and an electron or proton as my central charge. But now that we've written down the expression, we can figure out what the direction should be. Since the electric field is just K times Q divided by r squared in the r hat direction, when Q is positive, this is in the positive r hat direction. So for a positive charge like this, we'll need the direction to point outward. And actually, what we drew originally was also correct. For a negative charge particle, then we would have a negative r hat for our direction, so those will point towards that charge. Okay, we've got the right strength because it's varying. The closer you are, the denser the lines. So we've got that same thing for the strength. But the direction is a little bit trickier. It's not just any mass. It's got a sign to it now. We have a choice of positive and negative charges. So our direction we're going to take is we draw the lines towards negative charges and away from positive charges. That's completely consistent with this expression here, but it does have consequences. It means that we are indicating the direction that a positive charge would actually move as a result of that field.